So okay, now we will start the session. Right. Out of 5 modules, we were completed the almost 3.5 modules. So we are in 5th module right now. 4th module is pending. We will discuss 4th module in the next class onwards or after your CIE exams. Right. In the 5th module, we were completed the underground cables. Right. Up to the tick mark topics all are covered in the previous lectures. Right. Today, let us discuss about the remaining topics. So the remaining topics are only simple topics. So I think it is one class is enough for the remaining topics. So the topics are need of EHV transmission systems, types of DC links, and comparison between AC and DC transmission, advantages of DC transmission, and HVDC transmission systems in India. These are the topics remaining in this 5th module. Right. We are going to discuss about these topics today. So upon completion of this lecture, you can explain the necessity of EHV transmission system, and you can also explain the operation of HVDC system as well as HVDC links used in the HVDC transmission system. And you can also compare the AC and DC transmission systems. And you also summarize advantages for DC transmission system. And you can also list out the HVDC transmission system presently operated in India. Right. So we know that electrical power will be generated at generating stations, and the generated voltage will be in the range of 11 kV, 22 kV, 33 kV, sometimes even it is 6.6 kV also. So these are the voltage levels for generations. And the generated electrical power at the generating stations will be transmitted to the long distance through transmission lines, right? And then it is distributed to the consumer through distribution lines. So the transmission systems that are present are of 2 types. So which are overhead transmission, and the other one is underground transmission. So there are 2 transmission systems which are present. Right, overhead transmission lines are nothing but in overhead systems you will transfer the power through overhead lines. Right, in underground transmission systems you will transfer the power through underground cables. Right, we were discussed about the design of overhead transmission lines and underground cables already in previous modules. Okay, and if you observe the voltage levels for transmission, the voltage levels for transmission will be 66 kV, 132 kV, 220 kV, 400 kV, 765 kV. So these are the voltage levels for transmission level. Okay, so during transmission, there is no power will be tapped from the lines. Okay, so these are very high voltages. So at these voltages, no apparatus will work. Okay, so during transmission, you will not tap the power. Right. So then, if you observe the Okay, sorry. Right, ma'am. So up to what topic I discussed here. So my mic is in mute. Right here. So voltage levels for distribution. So these are 33 kV, 11 kV, 6.6 kV, 400 volts 3 phase, 230 volts single phase. You know this, right? So now depending upon the level of transmission voltage, the lines may be called as HT lines or LT lines. HT lines in the sense high tension lines, LT lines in the sense low tension lines. So these high tension lines will carry the power to industrial consumers, and LT lines will carry the power to residential as well as commercial consumers. Okay, right. So depending upon the level of voltage, sometimes you may be classified them as a low voltage, medium voltage, high voltage, extra high voltage, ultra high voltage. Okay, so sometimes the lines may be called as EHV transmission lines, or sometimes transmission lines will be called as ultra high voltage transmission lines, or high voltage transmission, like that you call, right? So depending upon what value you can call these as HV, EHV, or UHV transmission lines is depending upon the voltage level. Suppose if our voltage for transmission is 240 to 1 kilovolts, so then that line generally will be called as low voltage line. And if the line is having 1 kV to 66 kV voltage level, so then the transmission line is called the medium voltage transmission line, right? And if your voltage is between 132 kV to 300 kV, right, up to 300 kilovolts, you can call the transmission line as a high voltage transmission line. Okay, then 300 kV to 765 kV, right? If the transmission voltage is 300 kV to 765 kV, then that transmission line is called the extra high voltage transmission line. And if it is above 765, so in such a case you can call that transmission line as a ultra high voltage transmission lines. Okay, high voltage, extra high voltage, and ultra high voltage transmission lines. So these transmission lines are classified depending upon the voltage level. Okay, right. So if you observe the highest AC transmission voltage in India, so the highest AC voltage transmission level in India is 756. Sorry, 756, 765. Okay, this is mistake. 765 kilovolts is the highest transmission voltage in India, which is of AC, right? So if you observe in the worldwide, it will be having about 1100 kV to 1200 kV, right? So now in India, you are also having 1200 kilovolts ultra high voltage transmission line, right? But this 1200 kilovolts ultra high voltage transmission line will be there in testing case only. So it will be a testing station, so which is operated by the Power Grid Corporation of India, so which is located in Bina, Madhya Pradesh, right? So you can also transmit the power through HVDC transmission lines. The highest HVDC transmission line voltage in India is plus or minus 800 kilovolts. Okay, so the electrical power will be transmitted either as AC or DC, right? So if it is high voltage DC, the highest transmission voltage in India is plus or minus 800 kilovolts, and in the world it is 1100 kilovolts. So this 1100 kilovolts HVDC transmission system is there in China, right? So as we discussed in the previous slides, so the electrical power will be transmitted through long distance through extra high voltage transmission lines, right? So then what is the need of going high voltages for transmission systems, right? So if you observe the need for extra high voltage transmission systems, so these are the reasons, right? So when you use the extra high voltage, or when you transfer the power through high voltages, so then there will be a reduction in line current. Okay, so if the power is transmitted at a high voltage, so then there will be a reduction in line current. How it will happen? Let us see here. I had given you the equation for three-phase power. So this is the three-phase power. P is equal to √3 VI cos phi. From this, if you take the current I, so then I is equal to P by √3 V cos phi. So now from this relation, you can say that current is inversely proportional to your transmission voltage, right? If the transmission voltage is increased, the load current or transmission current, this current will decrease. Okay, so line current will decrease when you transfer the power at a higher voltage, right? So this is the first one. So when you transmit the power at a higher voltages, when the voltage is high, then line current will decreases. So when the line current decreases, what happens to the losses? Losses will decreases. So three-phase losses. So when you remember the three-phase power loss equation, so this will be equal to 3I square R. So this is the power loss equation. So W is equal to 3I square R. So here the power loss depends upon the line current. So resistance of the transmission line is generally constant. So if the current is reduced, so then losses also will reduce. So because of using high voltages, transmission line current decreases first. So then electrical losses will decreases. Okay. So now if the losses are decreased, so then what happens to the efficiency? Efficiency will be increased. Right? When you transfer the power at a higher voltage, transmission efficiency will increase. And you will also have the less voltage drops. So voltage drops across the transmission lines will be reduced. So when you transfer the power at higher voltage, so voltage drop across the line, if you write voltage drop, so this will be equal to I into Z. So impedance of the transmission line may be constant. So as the line current is reducing here because of high voltage, so then drops also, voltage drops also will reduce at higher voltages. So when voltage drops are reduced, what about the voltage regulation? So voltage regulation will increase. What is voltage regulation actually? If you are transmitting the power from one place to another place, right, which are at long distance through transmission line. So let us call it as receiving end, sending end voltage. It is the receiving end voltage. So then what is the regulation here? Regulation definition is change in voltage from sending end to receiving end, which is VR minus VS. Sorry. VS minus VR by VR. Okay. So now when the voltage drops in this transmission line is decreased, so then what about this difference? This difference also will decrease. So regulation will decrease. So that means regulation will be improved here, right? So always we have to we need less voltage regulation. Less voltage regulation is the best one, right? So whenever this transmission voltage is increased, current will decrease. That current will reduces the voltage drops across the line. So because of reducing voltage drops, the regulation of the transmission system will improve, right? So then you will be having a reduction in conductor material requirement. Okay. So when the line current is small, if the line current is reduced, so then automatically the conductor material which is required for transmitting the power will also reduces. Okay, and if the higher voltages high voltage transmission also increases the transmission capacity. So transmission capacity is represented with P is equal to VR VS, sending end voltage, receiving end voltage, by X. So X is the inductance of the transmission, right? So now if the transmission voltage is high, so then these two voltages will be very high. So this this voltage we are going to increase. Then what about the power? Power will also increases. That means because of using higher voltage transmission systems, transmission capacity of the line will increases, and you will be also having the low installation cost, and you will also have the flexibility for future expansion of the line, and it is also economical to interconnect the power systems at a extra high voltage transmission lines. Okay, these are the need or advantages. You can also call them as advantages, right? So need of EHV transmission systems or advantages of EHV transmissions are these. Okay, so now once if you observe this graph here, So the transmission voltage is represented by X, right? So now as the voltage level going on increasing, then the transmission line and terminal equipment cost, right? The transmission line cost and terminal equipment cost will go on increasing. Okay, so if you transmit the power at higher voltages, you need higher voltage capability equipments here. So if you want to use the earth arresters, surge arresters, lightning arresters, so these all the terminal equipment cost will increase as the voltage going on increase. Even the insulation cost also will increases, right? So the cost for terminal equipment will generally increase when you increase the transmission voltage. But if you observe the cost for energy losses, right? As I said before, when the voltage is decreasing here, losses will decrease. So when the losses is decreasing here, so because the cost for these energy losses will go on decreasing as the voltage level is increasing. Now if you observe the total cost curve will be like this. Okay, so now the minimum tow cost will be occurring at this point. So this is the most economical voltage level of the transmission line, right? As the transmission voltage is going on increasing, then the total cost of the system also will increase at a particular voltage. So this is the need about the EHV transmission system. And if you observe the advantages and disadvantages of EHV transmission system, right? What advantages? As I said before, the advantages for EHV transmissions are a reduction in line current. So this one is line current, and there will be a reduction in losses, and the volume of conductor material required is reduced, and there is a decrease in voltage drop. So because of decrease in voltage drop, voltage regulation will be improved, and transmission capacity and transmission efficiency of the system also will increase. Okay, transmission efficiency will increase, and power handling capacity also will increase because of this extra high voltage transmission system, right? So then if you observe the disadvantage of this extra high voltage transmission system, so the main disadvantages are corona loss and radio interference, right? So when you are going on increasing the voltage levels, so then the corona will form, right? This corona will be having some disadvantages on nearby communication lines, right? So there will be a radio interference with the this corona. So the details about this corona we will discuss in the 4th module now, right? Then if you see the another disadvantage, so it requires the high strength towers. So when the voltage level is increasing, so then obviously it requires the high strength towers. So electrical stresses will be more, right? Because of that reason you require the high strength towers here, and also you require the high insulation. So insulation needs, so when the voltage level is increasing, insulation needs will be increases, right? You require high amount of insulation, and so there will be difficulties in erection of these towers also. So when you transmit the power at higher voltages, so there will be some difficulties which occur during the erection of the transmission line. And it also the cost of the transformer and switchgear equipment will also increases with the increasing voltage levels. Okay, so even though there are some disadvantages and there are some advantages, so from this previous graph, right? So total cost as the transmission voltage is increasing, so the total cost of the car will be like this. So right, so now you have to observe the minimum point where the cost will be minimum, right? The minimum point at the minimum point, so what is the voltage level? That voltage will be the most economical voltage level. So that voltage you have to select for the transmission system. Okay, so this is about the extra high voltage transmission system. Okay, this extra high voltage transmission system is a AC transmission system. Okay, you will transfer the power from one location to another location with the AC current. right? So the next topic is HVDC transmission, right? So as I said before, the electrical power will be transmitted not only with AC, you can also transfer the electrical power with DC current also, right? Here you are having the HVDC transmission systems to transmit the power from one location to another location, which are very far away. Okay, so from one generating station and consumer station. Suppose if there is a long distance, generally this HVDC transmission system will be preferred. Okay, so in this HVDC transmission system, you will be having one rectifier and one inverter. Okay, you will be having two substations. So in one substation, you will be having rectifier, and another substation, you will be having inverter. So this rectifier station will be generally at the generating station. So the electrical power will be generated at a AC only, at generating stations in the form of AC only. So then after using the step up transformer, so you will step up the voltage, generated voltage to very high voltage. So you will be having high voltage AC at the secondary of the transformer. So then at the substation, which is having a rectifier. So by using this rectifier, you will convert this high voltage AC to high voltage DC. High voltage AC will be converted into high voltage DC, and the power will be transmitted in this DC only from substation to a location which is far away from the substation, generating substation. Okay, so the electrical power will be transmitted through HVDC line, right? So then at the receiving end, you will be having another substation in which you will be having inverter. So this inverter will again convert this HVDC power to HVAC power, and then by using one transformer, you will step down the voltage, and this voltage will be given to the consumers. Okay, so now this is the entire HVDC transmission system. Okay, you will the main components in this HVDC transmission systems are one rectifier station, one inverter station, and this is HVDC line. You can also call it as HVDC link also. Line or link, you can change that. Okay, so through this HVDC link only, you will transfer the power from one location to another location. Right. So now, what are the different types of HVDC links that are available here? Let us see. So before that, so you observe this graph here. So now, here we are taking the distance as on x-axis and total cost on y-axis. Okay. Distance on x-axis, total cost on y-axis. Now we are going to calculate the total cost of the AC transmission line as the distance is going on increasing, right? So as the distance is going on increasing, so this blue line represents the total cost of the AC line. Okay, so now as the distance is increasing, this red line will indicate the total cost of the DC transmission. As I said, you can transfer the power either AC or DC. So if you use AC for transmission, so the cost will be like this in the blue line. Okay, as the distance is increasing. So for DC, it will be a red line. Now, so these two lines are intersecting at one point here. So this point, we call it as a break-even distance here. Right? So at this break-even distance, at this particular distance, the cost of the AC line as well as DC line, both will be the same. Okay, so at this distance, you can prefer either AC line or DC line. So, but if you observe the below this break-even distance point, right, this side, if you observe here, this AC line cost will be lesser than the DC line cost. Okay, so now if your distance is below this break-even distance, so then in such a case you have to prefer the AC transmission. Okay, up to particular distance, AC will be the most economical when compared to the DC. Right? But after this break even distance, if you observe, then the DC line cost will be lesser than the AC line cost, right? So for long transmission line, very long distance, if you want to transmit the power, so then in such a case you have to use the DC lines. Okay, high voltage DC lines will be generally used for transmitting the power for very long distances. Okay, so why? Because the total cost which are incurred for HVDC lines will be lesser when compared to the AC lines. Because of this reason, the cost considerations you have to take depending upon the distance. So when the distance is very high, you have to go for HVDC lines. If the distance is minimum, then you will transfer the power through AC lines. Okay, right. So now what are the different types of HVDC links that are available? As I said before in this previous slide, here in this slide, you will be having one rectifier station, one inverter station. These two rectifier and inverter stations are connected through this HVDC transmission line or HVDC transmission link here. So now what are the different types of these HVDC transmission links that are available for transmitting the power, right? So there are mainly 4 types of links are available: monopolar link, bipolar link, homopolar link, and you will be also having back-to-back system. Okay, so these classifications are depending upon the arrangement of the poles and earth return here. Okay, right. So let us see the monopolar link, how this monopolar link will be. So in this monopolar link, so you will be having only one pole or one line here, right? And return path will be either earth or sea. Okay, so you will be in monopolar link, you will be having one pole with negative polarity. So one DC transmission line, if you observe. So pole in the sense you have to consider it as a transmission line, DC link. Right, this DC transmission line will be only one. So the conductor or pole. So this will be only one in case of monopolar link. So that to negative polarity. And the return path for the current will be done through earth here. Or you can also use the C as the return path for this power. Okay. So this is about the monopolar link, right? So in this monopolar link, you will also have one converter station, one inverter station here. So between the two converter and inverter stations, you will be having transmission line, which is of a monopolar. Okay. So generally, this type of monopolar link is not using presently. Right. So the next link is bipolar link or bipolar transmission system. Right. In this bipolar link, you will be having 2 poles or 2 transmission lines, which one will be positive, another will be negative with respect to the earth. Okay. So in this bipolar transmission system, you will be having 2 poles or 2 transmission lines, one as the positive polarity, another one as a negative polarity. So these positive polarity and negative polarity are with respect to earth only. And here also you will be having 2 converter station. One station is rectifier, another station is inverter. Right. So the midpoint of the converter. So here midpoint of the rectifier and midpoint of the inverter. So these 2 are earthed here. These 2 are connected to earth here. So midpoint of the converters are connected to the earth through the earth electrode. So generally, this is the most commonly used transmission systems which is presently used here. So another link is homopolar link. So in bipolar link, you will be having 2 poles. One is positive, one is negative. So in case of homopolar link, so the system also similar to the previous system, bipolar system. So but here you are using 2 poles with the same polarity. So generally the polarity will be negative. So if you observe the 2 transmission lines here, So these two poles are of same polarity. Here also negative polarity, here also negative polarity. So that because of that reason, it is called as a homopolar link. And the return path will be generally the earth here. Okay. So here also you will be having converter station and inverter station, and midpoint of the converter and inverter stations are connected to earth here. This earth will act as a return path. So another HVDC system is the back-to-back HVDC systems, right? So in this back-to-back HVDC system, you will not have the DC transmission lines. So there is no DC transmission lines present in this back-to-back transmission system. The converter as well as inverter stations both will be there in a same single substation here, right? So if you observe the first three, monopolar link, bipolar link, homopolar link. If you observe the first three, the converter station will be located at one place, and the inverter station will be located at another place. See here in this figure, monopolar link. So this converter station, which is a rectifier station also you can say. So this rectifier station will be there at the generating station, and this inverter station, converter 2, it will be there in the near to the load locations. Okay, so by these two are connected through this transmission line. So if you observe the monopolar link also, so you will be having one converter station, so which is a rectifier, another converter station which is inverter. So these two are connected to one transmission line. Okay, so here in bipolar link you will be having two poles with one as positive and another as negative. Okay, so if you observe the homopolar link also, here also you will be having two converter stations which are connected to one DC transmission line. Okay, so when you compare all these three lines with this back-to-back system, so this back-to-back system will not have any DC transmission line. So DC transmission line is not present in the back-to-back system, and also this rectifier as well as inverter. So both stations will be there in a single substation. Okay, at the same location you will be having a rectifier as well as inverter. So that means, so from generating stations to this converter station, the power will be transmitted through AC, and this at this substation, the power will be converted into DC, and then again it will be connected to AC, and then it will be transferred to the second system, so which is in the form of AC. Okay, so this is about the back-to-back HVDC system. Right. So then let us see the advantages and the disadvantages of DC transmission systems. So the advantages for DC transmission system, if you observe, so there are only two conductors are used in the DC transmission line system. So when compared to the AC transmission lines, in AC transmission lines there will be three conductors, and there is also no inductance will be present. So because of that reason, so there will be no surges in the DC transmission systems. And also because of the absence of inductance, so there will be less voltage drop in DC transmission lines. Okay, less voltage drop will be there in the DC transmission system when compared to the AC transmission system. So also there is no skin effect in DC transmission lines. So small cross-sectional area conductor is required for the DC transmission lines. So the electrical stresses that are observed in case of DC will be less when compared to the AC transmission lines. So because of that reason, the insulation required for the DC transmission system will be minimum. And because of this DC transmission system, there will be no interference will be caused with the nearby communication lines or systems. And if you observe the corona losses also very low when compared to the AC transmission system in case of DC. And in DC transmission system, so you will be generally not having any difficulties while synchronizing, and also you will be not having some stability problems also. Synchronizing problems and stability problems will be minimum in DC transmission system, and you will also not have any dielectric losses also. Right, so this dielectric losses will be observed when there is a capacitance parameter. right? In DC systems, you will not have inductance and capacitance effect. So because of that reason, there is no dielectric losses also present in the DC transmission system. Also, the DC transmission system is more efficient when compared to the AC. So because of that reason, rate of price for the towers, poles, insulators, conductors will be low. So DC will be most economical. So in DC transmission system, the speed control range is greater than the AC transmission system. So if you observe the AC motors as well as the DC motors. So AC motors will be maximum speed will be about 1500 RPM, right? Or mostly if you use 60 hertz of frequency, then the maximum speed is 3000 RPM. So but in case of DC, there is no limit for the speed control, correct? Higher speeds will be possible. So within the DC systems, right? So there is low insulation need for the DC transmission systems, and the prices for the cables also, DC cables will also be low. So insulation level required is low. So when the low insulation is required, DC cables will cost will be decreased, right? In DC supply system, the sheath losses in underground cables are also minimum. So this DC system is suitable for high power transmissions based on the high current transmission. The charging current in the DC transmission system also minimum. So these are the advantages of the DC transmission system. Okay, so there are a lot of advantages for DC transmission system. Suppose if you observe the disadvantages for the DC transmission system. So if you observe the disadvantages here, so we cannot step up the level of DC voltage by using the transformer here, right? In case of AC, you will use the transformers and you will step up the voltage levels. Okay, so but if you want to step up the voltage levels for DC, you cannot use the transformer. Okay, so there is a limitation of DC switches and circuit breakers, and they are also very costly. The DC switches and circuit breakers which are used for the DC transmission systems are having some limitations, some drawbacks are there. So and also the cost of the circuit breakers and switches for DC transmission system will be very high when compared to the AC system. Now, as I said in the first point, we cannot step up the DC voltage by using transformer. Suppose by how you can step up the voltage? By using a motor generator step. Right? So if you want to step up the DC voltage, then you have to use the motor generator set. Okay, so when you use this motor generator set, so then this efficiency of the system will decreases. Okay, motor generator set will be generally having low efficiency when compared to the transformer. So this motor generator set efficiency will be generally about 70 to 75% only. But when you take the transformer efficiency is about 98% to 99%, right? So if you want to step up the voltage, DC voltage, so the efficiency of the system will decreases. And also the DC transmission system is more complex and costly when compared to the DC transmission system. And the level of DC voltage cannot be changed. So as I said at this point also previously discussed here. So we cannot get the desired voltage for electrical and electronic appliances. So which are 5 volts, 9 volts, 15 volts, 20 volts, right? So suppose if your transmission voltage is very high, so this DC transmission voltage is very high, your appliances require this 5 volts, 9 volts, 15 volts. So this cannot be done by using this transmission DC voltage. Okay, so why? Because we are not having the small transformers. Okay, so transformers cannot work on DC. That you know already. So these are the advantages and disadvantages of DC transmission system. Now, if you see the comparisons, we were discussed about the advantages, disadvantages for both AC as well as DC. So now let us list out the comparisons, basic comparisons for AC as well as DC transmission systems. Right? So you take the number of conductors if you observe the number of conductors, so in case of AC, you have to use 3 conductors. In case of DC, you have to use only 2 conductors. And inductance and surges. So the inductance is not observed in the DC. You will not have the inductance in case of DC. And you will be having the inductance effect in AC transmission system. Right? So because of that reason, surges which are developed due to this inductance capacitance effect will be there in AC, and surges effect will not be there in DC. Okay, and if you observe the voltage drop, so voltage drop in case of AC will be very high when compared to the DC. So why? Because here in case of AC, you have to take into consideration the voltage drop across the inductor as well as capacitor. Right? In AC, you will be having resistance, inductance, capacitance. All 3 parameters will be there. So there will be voltage drop in capacitance, voltage drop in inductance, and also in capacitance. So voltage drops will be very high in case of AC. So, but it is low. The inductance and capacitance effect not there in DC. So voltage drop will be the drop across the only resistance of the line. And also here there are 3 conductors in case of AC. There are 2 conductors in case of DC. So because of that reason, so voltage drops in the conductors will be very low in case of DC transmission system. Now skin effect. What is skin effect? So when you skin effect is the non-uniform distribution of the current. Okay, so when you take a solid conductor, and if that solid conductor is supplied with AC, so then the current will take the outer layer. So the current is not uniformly distributed through entire conductor in case of AC. So that is called the skin effect. But that skin effect is not observed in the DC. Right? So when you transfer the power through the conductors, so that conductors are solid conductors, so then the skin effect is not observed. So that means there will not be non-uniform current. So there is always uniform current will flow in the conductor in case of DC. So then what is the need of insulation? The need of insulation required for the AC transmission system will be more. So when compared to the DC transmission system. And interference with the communication lines or nearby systems will be there in case of AC, and you will not have any interference with the nearby communication lines with the DC. You don't have. So corona loss will be occurring in case of AC, right? So corona loss will be there in AC. So even DC also you can observe the corona loss. So but it will be very less. So here they have written don't occur. So but corona loss will be there. Small amount of corona loss will be there in DC system also, right? So very low corona loss. So you need to the dielectric loss. Dielectric loss will be there when there is a capacitance effect, right? In AC transmission lines, you will be having the capacitance effect. In DC, there is no capacitance effect. So because of that reason, dielectric loss will be there in AC transmission, and it will not have the in the DC transmission system. Right, synchronizing and stability problems will be generally not observed in AC transmission system, and some it will be there in the DC transmission systems. And if you observe the cost of AC transmission for long distance, if you take, so this will be expensive. So if you want to transfer the power from one location to another location, so which is a very long distance, so then AC is expensive. For smaller distance, AC is economical when compared to DC. So, but for larger distance, AC is expensive when compared to DC. So, length of the conductors will be required will be small in case of AC, and it will be more. And if you take the repairing and maintaining cost, so then AC transmission systems will be easy for repairing and inexpensive also. So, but in DC transmission system, repairing will be difficult and also it is expensive. Transformer. So transformer is required only in AC and it is not required in DC. So these are the comparisons for AC as well as DC transmission systems. Right. So the last topic, HVDC transmission systems in India. So what are the different types of different locations in which we are having the HVDC transmission systems? in India. So we are having these HVDC transmission systems in India, which are presently in operation. So the first one is plus or minus 500 kilovolts and 1500 megawatts. So this HVDC transmission system is present between Rihand and Dadri. Okay, between the location Rihand and Dadri, we are having 500 kilovolts plus or minus, which is having a power rating of 1500 megawatts. Okay, and you will also have the another HVDC system, so which is a back-to-back station, back-to-back at the Vindhyachal. Vindhyachal, you will be having one HVDC transmission system. So the power rating will be 2 into 250 megawatts. Okay, so that means it is a back-to-back system. This is a bipolar link. So here two lines will be having, each will be having 250 megawatts. Okay, so another HVDC transmission system which is present in India is at Chandrapur. So here this Chandrapur also back-to-back station only. And another one is between Talchar and Kolar. So between the location Talchar and Kolar, so you will be having one HVDC transmission line. That HVDC transmission line voltage level is 500 kilovolts and power rating is 2000 megawatts. And you are also having the HVDC transmission line at Sasaram, which is a back-to-back station. Okay. So that back-to-back HVDC transmission system rating is power rating is 500 megawatts. And you are also having Gazuwaka. At Gazuwaka also you are having one HVDC transmission system which is a back-to-back station. So the rating will be 2 into 500 megawatts. And also you are having HVDC transmission system between Balia and Bhiwadi. Between the location Balia and Bhiwadi, you are having one transmission link. Right, that voltage level is 500 kilovolts and power rating is 2500 megawatts. So these are the HVDC transmission systems which are presently operated in India. So now if you observe these here, so if you observe this, we are represented two locations here, Rihand and Dadri. So if you observe here, we are having only one location, Vindhyachal, Chandrapur, Sasaram, Gazuwaka. Okay, so only one location is represented here. So, but here you are represented two locations, Rihand and Dadri. Here, Talchar and Kolar. Here, Balia and Bhiwadi. What it represents now? So, at these stations, so only one location in the sense. So that HVDC transmission system is the back-to-back system. As we discussed in the HVDC links here. So here the back-to-back system will not have any DC transmission line, and the inverter station as well as rectifiers will be both will be there in a same substation. Okay, that means back-to-back system will be having rectifier and inverter at a same station. So because of that reason here at Vindhyachal you are having back-to-back station. So inverter station as well as converter station, inverter as well as rectifier, both will be there at the Vindhyachal only one location. So this one Chandrapur back-to-back station also you will be having only one substation at which inversion as well as the conversion will take place at Chandrapur. Here Sasaram at Sasaram also you are having back-to-back station. So but here this Dadri HVDC transmission line, so Rihand and Dadri, so this is not a back-to-back system. So it may be a bipolar transmission line system. Okay, plus or minus we represented here. So this is a bipolar transmission line system. Okay, so now this Talchar and Kolar transmission line is a only one single pole, single power represented here. So this is a maybe monopolar. So monopolar transmission line. So which is between Talchar and Kolar. So this is also a monopolar link which is between